Good morning, everyone. This presentation is about power factor correction. So this is my background. I worked for NEC and Renesas for more than 15 years, mostly around microcontrollers. My focus is on motor control and power electronics. Industrial experience before that, I worked in electronic detection systems, and then 5 years in a power generation plant in Romania. My education is I have a master's degree from San Francisco State University and a diploma engineer degree from a university from Romania. So this is the Renesas portfolio of products. Renesas is mostly known for microcontrollers, but we also have system LSI and analog and power. The portfolio of products moving forward since we merged, as you know, NEC and Renesas merged in 2010, and the products were basically the two companies' products. And what we had the Super H, the V850, the RX, the 78K line, and also we have the R8C. Moving forward in towards 2013, some of these products will be basically they're merging into other new products. For instance, the 78K line with the R8C merged into the RS78, which is the low-end Renesas product, 16-bit. Then we have the RX family, which covers previously the V850 and the RX. And then we have the high-end, which is the RH850. That's a combination between the SH and the high-end V850. And also have the embedded security ASSP. Enabling the smart society requires multiple efforts among various industries. And one of the major parts of it is managing energy production and managing energy efficiency. As you know, conventional resources are very scarce, and they're becoming more and more expensive. And the new energy resources, the green energy, so to speak, is not cost effective yet. So I think the most cost-effective step we can take today is to try to conserve energy and improve the energy production, energy distribution. So energy efficiency is key to enabling the smart society. And one of the aspects of energy efficiency is power quality. As you know, a great number of loads or consumers are motors and power supplies and so on. So, and what happens with power supplies and motors, they degrade the power quality, something that what we call power factor. So power quality is also a key factor in enabling energy efficiency in power distribution, power management. The agenda today will be basically we're going to look at the market drivers for power factor correction. We'll look at what is the basics of power factor correction. We'll look at what is power factor, what is bad power factor, how does this impact in the industry, the distribution, and the consumers, and then we'll start looking at how we can correct the power factor, bad power factor. We look at the basic power factor correction topologies. We will look at the Renesas solutions. We will look at what Renesas can offer. We have both, as you can see, as you will see, we have both analog and digital solutions. And we will look in particular to a digital solution implementation. So let's look at the market drivers for power factor correction. As you may know, some of the energy is delivered, but it's basically not used, which means it's wasted, right? And this is due to the bad power factor. Another factor in the market and driving power factor correction is the consumer. Some consumers are charged for bad power factor, and these are the industrial and commercial ones. The residential ones, they are not charged yet, but with the development of the electric car, at some point, probably or most likely the utilities will start charging the residential consumers. Power utilities need to cover for those consumers that don't pay, that are not charged for bad power factor. And of course, one of the, as you will see, one of the aspects of bad power factor is that it overloads the distribution line. So for that reason, the power utilities will have to compensate for these losses by increasing the size of the distribution lines, transformers, and so on. Also, with bad power factor, you also have harmonics, and these are mostly generated, because of the switching elements in power supplies and so on. And these harmonics can disrupt the consumers if they get back to the line. And also, another aspect is the government. The government is also pushing for better power factor, all over the world. So what is power factor? If you look at the typical AC source and load diagram here, so we have a motor connected to the 120 volt AC line, and we have a watt meter and we have an ammeter. Okay, if we look at the power consumption, we'll see that the watt meter is going to show 400 watts, but if we calculate the power based on the current and the voltage on the input, we end up with 612 VA, which is called volt ampere. So it looks like there's some kind of power loss somewhere. So the power that is delivered from some of the power that is delivered from the source to the load, it's somehow lost, right? So the power factor is this ratio between the real power, which is the power at the motor, over the input power, which is called the apparent power. So if we, the ratio is the power factor, and in this case it's 0.653. Ideally, we want to have this power factor equal 1. That's when the power that is generated is used 100%. Let's look at the power factor. Let's look at some waveforms here. So where did the power go? Here we show the AC voltage and AC current, and the effect of bad power factor is the displacement. And this is caused by the inductive loads like motors, transformers, and so on. Another way of looking at it is with the power triangle. So the ratio between P and S, it's what's called the displacement power factor. And this is one aspect of power factor, one component. This is the cosine of the angle between the voltage and current. So the range is, as I said, from 0 to 1. And the other component is the reactive power. And then, of course, when the reactive power is 0, then we have, the displacement power factor is 1, that's what we want. This reactive power is the power that is used for magnetizing the motors and the transformers. And basically, this power is not used for producing any kind of real work. So, another aspect of it is the total harmonic distortion. Nonlinear loads, such as switching power supplies and so on, cause a distortion of the current. So now you can look at this as a combination of the displacement and distortion of current. So there's two components. The THD, or the total harmonic distortion, is calculated as a sum of the squares of different harmonics up to the 39 over the it's a square root of that over the fundamental, and these are RMS values. So the total power factor correction, total power factor is a combination of displacement power factor and the THD. Let's see what causes power factor degradation. As we said, inductive loads will cause a current lag behind the voltage, and then the nonlinear loads with switching elements will distort the current and will introduce harmonics. So again, total power factor is the displacement, a combination of displacement and THD. Bad power factor is what is less than 1. Okay, I have a question here for a t-shirt. Let's see, what causes power factor degradation? A, resistive loads. B, inductive loads. C, capacitive loads. D, nonlinear loads. E, B, C, D, or none of the above? Who said B, C, D? You go. Thank you. Did anybody say the same thing? I'm sorry. I didn't see you. I couldn't hear you. Okay. So why power factor less than 1 is bad? Well, as I said, reactive energy is not used to produce real power, right? If we have a distribution here, driving some motors, as I said earlier, because of the bad power factor, we're going to have some IR losses on the distribution lines, right? Because we supply more power, but we use less. So even though the consumer, the consumer needs to drive his appliance with some power, but he's basically the utility is sending him more power. So there will be some IR drop on the line. So the utilities will need to compensate for that in some way by oversizing the distribution lines. And then the other aspect is the harmonic. The harmonics will propagate back into the line and will cause some disruption to other consumers. Power factor correction. So now we have to look at how we can correct the power factor, bad power factor. So this is the problem we have. We have AC current lagging behind the voltage, and it's heavily distorted. So ideally, what we need to do is bring back the current in phase with the voltage and reshape the waveform into a sinusoidal one. So basically, we need to make the load look like a resistor, right? Because the resistor does not affect power factor. So this is what we're going to have to end up with. So need to control the current to make it sinusoidal again and reduce those peaks. So power factor correction methodologies. First, I mean, one way to look at them is as being passive or active. Passive meaning that we're using passive elements to correct the power factor, such as inductors and capacitors. And then we have active power factor correction when we use active components such as amplifiers, switches, MOSFETs, diodes, and inductors. A typical passive power factor correction circuit, it's shown here. And basically what we have, it's a filter on the input, which is used to filter the harmonics. Drawbacks, they're bulky, and also they can't adjust to the voltage on the input. Normally, you would want to have a constant voltage on the output. But in this case, as the voltage rises on the input, it's going to rise on the output as well. So it can't adjust to the input voltage. So this is the simplest one. And then let's look at the active power factor correction. So we are using active elements to shape the current. This is a typical boost converter topology where we have an inductor. Then we have a switch here. We have a diode, and we have a bulk capacitor. The way we drive this is basically we drive the gate of the switch with a PWM signal to charge and discharge the inductor into the capacitor through the diode. There's some issues here with efficiency, right? Because we have switching elements and we have active elements. So the switching, the efficiency will be affected by the switching losses on the transistor and also by the diode recovery current. Another way of looking at it is the type of switching we employ. One is called the critical conduction mode. So let's look at the circuit. Basically, the way this works is that transistor is switched on and off with a PWM signal. And there will be a current through the inductor like this. So basically, when you switch it on, the current is going to rise through the inductor. and at some point it's going to hit the maximum. And then we turn it off, and then the current is going to go down. And then when it reaches 0, we turn on the transistor again. This is called critical conduction mode because we let the current reach 0, OK? So for that reason, the ripple current tends to be high, right? So this kind of topology is not recommended for high power applications because you're going to have a huge ripple. It's mostly used in low power application. One advantage of this is that there's no recovery current through the diode because when the inductor reaches, the current reaches 0, there's nothing to discharge. So we can use less expensive diodes here, just silicon diodes. The active topology, another active topology is the CCM, or continuous conduction mode. In continuous conduction mode, the ripple current is very small because we basically control the ripple through the inductor in such a way that we don't let it reach 0, right? So this is more suitable for high power applications. The only thing is that now we have to deal with the diode recovery current. So one way to fix that is to use silicon carbide diodes, right? But obviously, those are a little bit more expensive. So there's a trade-off. So let's look at the typical implementation of a critical conduction mode power factor correction topology or circuit. What we have here is we have the switch, we have the inductor, and then we have a secondary which we use to detect the 0 crossing of the current. So when the inductor current discharges, we need to detect when it reaches 0. The way we do that is we use the secondary here for the PFC inductor, and we input that to a comparator on an MCU, for example. So that comparator is interlocked with the timer. So the timer, basically, the comparator is controlling the timer output. So when we reach 0, okay, the comparator is going to detect that situation, and it's going to turn on the timer output, right? So if we look at this diagram on the right, when we turn on the transistor here, the current rises up to a maximum, and then we turn it off. This has critical conduction mode topology has fixed time on for the transistor. So basically, we end up with instead of a PWM, there's a PWM, but it's variable frequency instead of variable duty cycle. So when we reach the peak, I mean, when the time expires here, we reach some peak value, and then we let it coast or discharge. That discharge point or 0 point is going to be detected by the comparator, and then we turn on again, and the cycle repeats. So this is called critical conduction mode, again, because we let the current reach 0. And then other things we need to watch for is the output voltage. So we need to maintain a constant voltage somewhere in the area of 400 volts or something like that. So that has to be detected by the ADC, and there's a controller here to maintain the output voltage. Okay. Another way of looking at it is the number of channels we employ. Okay. So we can have single channel where we have one set of elements, like inductor, transistor, diode, and so on. So when you see on the right, transistor turns on. This is the ripple current through the inductor. Other topologies use multiple channels. This could be 2-channel, 3-channel, and so on. So now we have two sets of inductor, diode, transistor, right? The net effect, okay, one thing about this is that if we control these 180 degrees out of phase, we end up with low ripple current. Okay, so the two individual ripple currents they try to cancel each other out. So we end up with a very small ripple current. Okay, so now we can use this for a higher, higher power application because we have less ripple current. Effect on high switching, high frequency switching. So if you have a circuit, a PFC circuit, we have these high frequency switching that is happening on the transistor and the inductor, and these can propagate back into the line, and they can disrupt the consumers. Actually, there are standards for that, so we need to somehow control this, through filtering, of course, and this is one of them. It's called the light filter. So this is basically something that many people use, and they have to because otherwise they will not pass certification. So higher ripple current will require better filters. Now you'll see later if we have smaller ripple current, then we can reduce the filter size. So let's look at the advantages of interleaving again. So reduce the ripple current. The size and number of components, well, the size is going to be less, but the number is going to be, it can be double or triple. But, that may be cost effective because smaller components are cheaper, right? Overall efficiency is increased, of course. And then so this is a typical circuit where, because of the interleaving, we can cut back on the filters, number of stages. So basically, it is in a way a cost-saving solution. So so if we look at the single versus dual interleave. So what is single channel? We can we have our inductor ripple current, which is can affect the size of the bulk capacitor, the inductor, and so on. And then we're going to have high current through the IGBTs. So basically, we're going to have some conduction losses that we have to deal with. The two channel, because we have two sets, they're smaller. They may be less expensive because they are driven 180 degrees out of phase. We end up with a smaller ripple current, which means that we can reduce the size of the inductors and the bulk capacitor and so on. We'll have better efficiency because we have smaller currents. So less conduction losses, and then further we can improve this by adding more channels, multiple channels for interleaving. Looking at the two solutions, side by side. For instance, ripple current, it's smaller on the two-channel interleaved, so that's a win. And inductors, smaller, maybe less, possibly a win. Transistors, two smaller ones. The diode, here we need to have maybe a silicon carbide, which is more expensive. And then the EMI filter smaller, efficiency is better, bulk capacitor smaller. So yeah, so basically there's an advantage overall to interleaving. So a typical application where you need power factor correction, as I said earlier, is motor control. So here we have a three-phase inverter, right, driven by the microcontroller, which has to drive the gates and detect currents, measure currents, and then we have a front end with power factor correction here, boost topology, and we have a power factor correction controller IC. Okay, so that's one way to do it. Another way to do it is to use the MCU. In this case, we're talking about what we call digital power factor correction. The previous one was analog. So the MCU can do basically both. As you know, most modern MCUs have many peripherals such as timers, and they can do such a thing. So basically, now the MCU will drive the motor and also will drive the power factor correction. And key to it to have is have enough timers and have enough ADC inputs and have enough performance to do this, because now you're going to have to deal with with two controllers, right? One controls the motor, the other one controls the power factor correction, and both of them are, they have internal PI controllers, and you need to make sure that you have enough bandwidth to do that. So Renesas offers actually a variety of power factor correction, solutions. We have both analog and digital. We have analog ICs. We have both topology CRM and CCM, single channel and interleaved, and then we have also this internal MOSFET driver. So one of the advantages for analog would be that they have internal MOSFET drivers. With MCU, you're going to have to use an external one. With digital, of course, MCUs with high performance MCUs, such as, we have a line of the RX, which, it's 100 megahertz chip with 10 nanosecond, single clock access to the flash. And it has internal PGAs and comparators, so that helps actually to reduce BOM. It has high-speed ADC. It has some hardware protection built in, for to detect fast if overcurrent situations and shut down, the system, and then has fast interrupt response. So let's look at the analog solutions. So as I said, the controls are both CCM and CRM. Beside that, okay, we have the superjunction MOSFETs for high frequency over 50 kilohertz and for up to 2.5 kilowatts. We also have high speed and low VCE on IGBTs for lower frequencies but higher power. So we have controls and we have switches, and we also have silicon carbide diode. Of course, support material such as application notes, documentation, and so on, and technical support. These are the analog parts listed by part number. CCM, CRM, interleave, single channel, and then list of features, and then the applications, the recommended applications. This is one of the analog chips for power factor correction. It's the 2A20114 and 2A20104. The difference is that this one it can work with current transformers. So some of the features are phase drop. This is an interleaved switch, right? Interleaved power factor correction device. At lower power levels, you can further reduce your losses by switching off one of the channels. So this is called a phase drop signal. So you can drop one of them because now you're at low power levels. Then there's an internal external clock can be used for that, and then also, as I said earlier, you can use current transformers for this. So this is one. And then we have the CRM, or critical conduction mode chip. Again, there's some part numbers here. This one also has phase drop. So you can, it's called a slave or master drop. So again, you have a slave and a master. And then in lower power situations, you can turn one off. And that way you can save some efficiency. Okay, so increased efficiency at high loads because of the phase drop. And then protection circuits. It's important, very important in high power applications to have protection because or controllers in general, MCUs can't respond fast, so you need to have hardware protection, which is very important for brownout, zero current pin opening detection, and so on. So if anything goes wrong, you need to be able to shut your system down as soon as possible. Okay, CCM interleave PFC control. So you can see some of the features like protection for zero current detection, open short. So this is the detection of the current through the inductor. You need to make sure that you are able to detect when something goes wrong timer latch, ramp charge current, brownout, soft start, so on. And gate drivability, it's important. This one happens to have a large, drivability feature, 1.2 amps, and so on. So now let's look at the digital solution. Digital solutions are when we use a microcontroller to do the power factor correction. So this is the typical diagram where you would have an input of universal, what's called the universal voltage from 85 to 264. And then you need to generate a 400 volt DC. So you have a microcontroller doing that, controlling the input ripple current, and then driving the PWM. I mean, detecting the ripple current or measuring it, driving the PWM, the gate of the switch. And then you have to have an input for the VAC because this has to adapt to various voltages. So you can use this everywhere in the world, right? It has to be able to adapt to that automatically. And then it's a VRF, which is going to set the output voltage. So this is a typical kind of a block diagram. So let's look at what kind of control functions do we need to implement in a digital power factor correction system. First of all, one thing that we need to monitor and control is the output voltage. So we need to make sure that we have 400 volts all the time, right? For that, we need to have a feedback from the output. And of course, the output will be a constant DC bus voltage. Then we need to also adapt to the input AC voltage, which can be from 85 to 264. So we need to measure the input voltage, and we need to be able to adjust to that automatically. We need to control the ripple current. For that, we need to basically look at the IGBT current through the sensing resistor, and also we need to account for the AC voltage. So that's controlling the ripple current is going to have to be a combination of the IGBT current reading and also the AC voltage input. And then, of course, the inductor ripple current is the amplitude of the inductor ripple current is the output, and we need to be synchronized with the ADC. Hardware protection. As I said earlier, it's very important to have hardware protection in a power system for overcurrent, overvoltage, under voltage, and we need to make sure that we can disable or shut down our power switches right away. Typical digital power factor correction circuit for a motor control. So we have a microcontroller. This happens to be the RX62T, which is going to be, we developed a reference design with it, and this is a 100 megahertz chip. So it does the motor control and it does the power factor correction. This is the reference design we developed, and as you can see, there's two sets of inductors and switches, and this is the silicon carbide diode, which is a die with two diodes in it. So these are our, there's the MCU here, the RX62T, and these are the power factor correction, channels interleaved. This is another look at it. So again, we identify the MCU, we identify the two channels. We also highlight here the Renesas IGBTs. So we use not only the MCU, but we have Renesas IGBTs, and we also have Renesas silicon carbide diode. System specification. So we developed this reference design with the RX62T, which is a 100 megahertz MCU, and the topology is a continuous conduction mode, two-phase interleaved. We use Renesas IGBTs. We have an input voltage, which is it's a universal input. We have an output of 395 volts, maximum output current 3.8 volts. Power handling PWM frequency is 35 kilohertz. It's two-phase, so it's 180 degrees out of phase with each other. The efficiency is 96%, and the power factor is better than 90.96. This is a block diagram of the various peripherals used for this PFC implementation. So first of all, we have the hardware elements such as the timers. So these two timers driving the gate of the switches, of the power switches. There's the ADC, which has to measure the currents on the sensing resistors and also the voltage on the output. And then we have the 10-bit ADC, which measures the AC voltage on the input. Then the protection elements. We have over voltage protection, over current protection, and so on. And then the software part, which is the current control and the voltage controller. So we need to have PI controllers or some other type of controllers for both the current and the voltage. As you can see, the voltage is the one that sets this. It's an inner loop. It's an inner loop here, and then is an outer loop. So the voltage is going to set, the voltage controller is going to set the reference for the current controller. Implementation. So we have the current sensing 1 and 2, the VAC and the feedback voltage, and then we have the voltage controller, and we have the current controller. So we have a target voltage set here, target set, and then we have the feedback, and then we have the controller, and the output of the controller is multiplied with the AC voltage because we need to follow the AC voltage wave or shape because we need to control the current so that it was going to follow the sinusoidal shape. So the way we implement the control loops, we use IR filters. Okay, so for each of these controllers, we have this kind of topology versus the PID controller. So it's another way of implementing control, closed loop control. The program flow. So we have a main and we have an interrupt, which is generated by these two timers called the GPT timers, which drive the MOSFETs or the IGBTs, and these generate an interrupt, right? And then there's a conversion starting, VAC and the current sensing and feedback. And there's a voltage, ADC voltage, to voltage calculation, voltage controller, current control, and the PWM update. So after we calculate the new values, we update the PWM. The resources used for the RX62T are the two timers, okay? For the gate drive, there's ADC for the voltage sensing, current sensing, and the 12-bit ADC, and the 10-bit ADC for the AC voltage input. So now we look at the diagram. It's like a block diagram, of course, to see how we use the peripherals on the RX62T. So the two timers here, 16-bit timer, GPT0, GPT1, driving the gates. And then we have these current sensing from the IGBT back to the ADC, and then we have the voltage on the output through this basically it's a repeater, but so it's a divider here, and we bring it back to the 12-bit ADC, and then we have the input voltage, right? The AC voltage or the rectified AC voltage to the 12-bit ADC. Since this microcontroller has internal amplifiers and comparators, basically we can get rid of these, right? We don't need this. We can bring these directly to the internal amplifiers, right? So this offers us a cost-saving solution. And then you can see on this side here, there's this part is the motor control part, which we don't talk about here, but just shows you how complex this device is. It can do the power factor correction, it can do the motor control. So the gate drive has to be synchronized with the ADC, right? And the way this is done is at every peak of the timer, right? We start sampling ADC, right? And then on the other phase or the other channel, every peak we start sampling the other ADC, and so on. So we alternate, between the two timers, 180 degrees out of phase, and this is how we sample the currents. The voltage, of course, is sampled at every peak of the timer. So it's a timer that counts up and down, right? And this is the gate signal for IGBTs. Protection. Protection can be implemented in two ways. One, external, where you don't really care what the MCU does, and you make sure that you have circuit on the outside to shut down if there's a problem. And the other way is to get the MCU to do it. In this case, we have implemented both. So basically, we have the PWM output as a comparator here, and the PFC output, and then we have these gates. These are the drivers for the gates, right, for the IGBTs. So we have this logic here to basically disable the signals. At the same time, we input this signal to the PoE pin, or port output enable pin, which internally it's a hardware feature which will internally disable these outputs. Right? So there's two ways we're doing it here. It's very important to have very solid protection. This is the ADC block. One of the highlights of this microcontroller is that it has multiple channels with sample and hold. Actually, we have 6 on this chip, but we're just showing ADC unit 0, which has the programmable gain amplifier on the input for each signal, right? Except for the input voltage, which is not that critical. And then we have sample and hold, meaning that we can take a snapshot of the currents at any time, and we get 3 different values, right? And it's very fast. Actually, it's a 1 microsecond conversion time per channel. Implementation with a timer. So as we said earlier, we use 2 16-bit timers to drive the gates. And these are GPT-0 and GPT-1. And then, these are the timers, and these are the gate drives. And as you can see, again, 180 degrees out of phase. And the frequency, the PWM frequency, is 35 kilohertz. So example of PFC control by GPT-0. So let's look at this is a timer. Okay, so this is one channel. It counts up and down. And then at some point, there is a compare register with this value. And what happens is when the timer value is equal to the compare register value, we basically turn on the output, which drives the gate. Okay. At the same time, we trigger the ADC. So when we trigger the ADC conversion is going to take some time, okay, which is here. So we start the ADC, and then it takes some time, right? And then we have an end of conversion. And at the end of conversion, we have an interrupt. That interrupt will trigger my control loop processing. So now we end up with a delta t, which is going to be the time it takes for the controllers to execute and finish the calculation and update the PWM. And that's going to be one of the measures of how efficient or how much the CPU or the MCU is occupied with processing the PFC signals. So we have PFC control start and PFC control end. Now, this is a real measurement done on this reference design. So as you can see here, we have, this is the 28 microsecond. This is the 35 kilohertz PWM frequency. Okay, doing this, we have two processes. For the first channel and for the second channel. And then these take each 4.5 microseconds. So within one cycle, we end up with 9 microseconds, which amounts to about 32% of that CPU occupancy. So 32% is what we use, we end up with for the power factor correction. Some waveforms here. So this is what it looks like, AC input voltage. input current, and then this is the inductor current, which has all this, this is the ripple that you can see here, and then it's the output voltage. Here is another device that has what we call high resolution PWM. So with the C03I, we have only 16 bits of resolution, right? So with this device, we add another register here, which has extra 5 bits. What this does, basically, we are controlling the edges on both sides. So effectively, we end up with 21 bits of resolution, meaning that now we have 312.5 picosecond resolution at 100 megahertz. Right? So this is very important for power supply design, where you want to control very precisely, the output, and this resolution, this gives you a very, very tight control of the output voltage. Okay, questions. I have a question for you. So what PFC method is used in the Renesas digital reference design? A, single-channel PFC in critical conduction mode. B, single-channel PFC in continuous conduction mode. Dual-channel interlead in continuous conduction mode, or none of the above. There you go. So summary, we looked at the market drivers for power factor correction. We looked at what is power factor, what defines power factor, what causes the power factor degradation, what kind of impacts bad power factor has on consumers and distribution. We looked at the basic topologies. First of all, we established that we need to correct power factor because, several reasons, utilities, consumers, and so on. Power that is lost, some of it is not paid for. Then also we have problems with harmonics that will disrupt other consumers. So we looked at the basic power factor topologies, and then we looked at the Renesas solutions. We have, as you know, both analog and digital, and we also looked at the implementation with a microcontroller. Okay. Thank you very much. Thank you.